Yet. Okay. Hey, so my name is Moira Tagle. I'm a senior software engineer here at WePay, and I'm going to be talking about our MySQL CDC streaming architecture. So here's a little bit about what we're going to go through. I have a lot of slides and not a lot of time, so I may speed through some of these. I'm going to start off by talking about WePay and why we built this particular real-time data warehousing solution. I'm going to talk about the components of the architecture. So we'll start off with Debezium, then we'll go to the Kafka to BigQuery connector, and then I'll talk a little bit about future work we still have to do, and where we imagine this going in the future for our particular use cases. So let's get started. So WePay's use cases, I don't want to talk too much about the benefits of a data warehousing solution. I feel like that could fit an entirely different talk. So hopefully you're already on board with the idea of data warehousing. But traditionally, a data warehousing ETL solution will be something like what we had before we created our real-time streaming solution, which is that you have a bunch of jobs that run on a particular schedule. Maybe you do only complete loads. Maybe you're a little bit clever and can do some periodic incremental loads. But incremental dumps have to be based on something, probably modify or create time. But this system has a number of issues. First is just that having infrequent loads means that in your data warehouse, all the data there is really high latency. It's not real time. It's potentially stale. It really means that a number of use cases you might like aren't really things you can do. There's just a ton of jobs for this. In our case, we have several jobs for every single table we want to load into our data warehouse. Any table or row with bad create or modify times can cause serious issues if you're doing these incremental loads. This whole system is completely incapable of dealing with hard deletes unless you're doing a complete load that overwrites the previous data every single time. We found that MySQL's replication latency could sometimes cause data quality issues. A particular slice might absolutely miss just like one row, depending on how much latency there was in the replication. Periodic loads put a lot of load on MySQL. We could get timeouts. And any changes to the MySQL schema don't propagate to the data warehouse automatically, which just means that you have to deal with that manually, which is a real pain. So this all led to us wanting a real-time solution. These are the basic components. We'll go through all of them a little bit. So I want to start with the sort of the first half, the MySQL to Kafka part. So we use Debezium, which is, just go over Debezium briefly. Debezium is streaming for your database changes. I'm specifically going to be talking about Debezium for MySQL, which is what we use here, obviously. So Debezium creates a Kafka event for every single database change. In the case of MySQL, it does this basically by tailing the log of all the database changes. And in the case of MySQL, thankfully, every single database change event has a ton of information attached to it. So when you are basically going through this log and taking every single event that shows up, you get a lot of information. So that's sort of the before and after here, every single database change, and also this operation and when it happened. So we have the complete information about the row before, after the change, what the specific operation was, and when it happened. In the case of Debezium, we also get all this nice metadata. We know exactly what server this came from. We know what GTID this particular event was associated with. Various other stuff there that I won't go into, but we get a lot of nice metadata that's potentially useful. So some finer details of Debezium. So the bin log events obviously are just for events. You probably do not have you know, forever retention for your bin log events. So when you first start up a Debezium connector, you probably don't want to just start reading from the bin log. You probably want to get a complete idea of what your data looks like in MySQL, and then after that's done, start reading from the bin log. So what Debezium does is when a connector is first created, it will take a snapshot of all the configured tables. It basically does this by grabbing a lock, reading all the information from the configured tables, and putting all those as if they are regular events into Kafka. So one fun thing is that generally for other databases, if you ever want to modify a connector to add a new table, you have to go through this resnapshotting process all over again for every single table in the connector. In the case of MySQL, we actually implemented a feature that you can configure in Debezium that allows you to be able to change a connector on the fly. Debezium will notice that a new table was added, and it will only snapshot that. It will do it in parallel, so your other events will continue reading from the bin log. When the snapshot completes, that table will start reading from the bin log, and eventually they'll merge together. You'll just have one unified connector again. Okay, a couple of things. So we still may need to rebootstrap our connectors. One big reason we may do that is if, God forbid, there is like a data quality issue, some event was lost somehow, we reserve the right to rebootstrap our connectors. So any client of the Kafka data needs to be able to handle a periodic message spike of all the snapshot info, basically everything in the table all over again. Some things about database definitions. So we're generally talking about DML here, but Debezium will also log all the DDL. It's stored in a separate Kafka topic. Yeah, if you're using Kafka, obviously, there's also the Kafka schema registry, though. So that's honestly what we use. So this technically could allow you to capture any database schema event changes that happen. But since we also have the Kafka schema registry, we just use that, and we look for changes in the schema registry to update in the case of backwards compatible changes, rather than trying to derive what should change based on the DDL. Okay, so I want to talk a little bit about how we actually set up the architecture for Debezium. So this is a really super naive approach. You have MySQL directly connected to Debezium, which puts stuff into Kafka directly. But I feel like we can all already see some problems with this. So this isn't actually what we do. Akshat before was talking about Debezium replicas. In case you're wondering what the deal was with that, we actually have Debezium read from specific to Debezium replicas, so we don't actually have to put any load on the primary MySQL database. And because duplication is better, we have 2 of them. And we don't actually have, obviously, Debezium connected to just one. We have a proxy in front, so Debezium can switch off between them depending on if one dies. And all these, so we don't actually just have one MySQL. Each microservice will have its own, but they all will replicate to the same 2, and so on. And then in the case of Debezium, each connector has its own, each microservice has its own Debezium connector. So I guess I'll just let you look at that for a second. So this is the final sort of architecture of how we have this whole thing set up. So here are a couple of uses for the Debezium pipeline. I said I didn't want to talk too much about ETL, but this isn't specifically just useful for ETL. So obviously, it's not specifically just useful for data warehousing. So it gives us data warehousing, which is great. In our case, it also is helping migrate us away from a monolithic database, because the microservices can publish events to Kafka, and then we can have a consumer consume those events and put those events back in the monolithic database. So that way we can move things out of the monolithic database, but anything that depends on reading from the monolithic database, it seems like nothing has changed. We can also use this to run data quality checks on our data, which is nice. Other potential uses of this is the whole Debezium pipeline, remember, gives you change data capture. So we can do this to do auditing on any change that has happened in a production database. And potentially also other services may be interested in database events directly. And because this is all going into Kafka, you can subscribe to those topics and get those events and do whatever the heck you want with them. Okay, so this is getting everything into Kafka, but we don't want to just leave it there. We want a complete replica of our data in our data warehouse. So that's where Kafka Connect BigQuery comes in. So if you're not familiar with Kafka Connect is streaming to or from Kafka. It was built specifically for ETL, which is great. And there's lots of existing connectors, but it's open source, and you can also build your own, which we did. So this is the Kafka BigQuery sync connector. We call it we call it KCBQ for short. Sync in this case just means that it is, taking data from Kafka and moving it somewhere else, rather than a source, which we're doing the opposite. We're putting data into Kafka. All right, so talking a little bit about BigQuery. BigQuery is Google's data warehouse. It has a streaming insert API, which is really useful. It allows us to take advantage of the fact that we're streaming data into Kafka in the first place, and the fact that obviously events from the source MySQL are happening whenever. The streaming insert AI is append only, but that's totally fine for our particular use case. So here we have a number of features of Kafka Connect BigQuery. So it has configurable retry logic. That's not strictly necessary for a Kafka connector. Kafka connectors have their own sort of retry logic. However, if you let a connector sort of do its own retry logic, it involves a lot of rebalancing, and that's it's just very expensive and annoying if it's not necessary. And we found that BigQuery has just a lot of transient errors. So why do this whole rebalancing, recreating the whole job, resending it, yada, yada, if when we get one of these transient errors, we can just wait a couple of milliseconds and try again. So schema updates, I mentioned that one of the problems with the traditional ETL system is it doesn't deal with updates to the source tables very well, or the source schemas particularly well. So in this case, what we do, we will actually, as much as possible, we will update the BigQuery schema as necessary. There are certain limitations to this, but I'll talk about those a little bit later, I think. Actually, I'll talk about them now because I can't remember if I put them in here. So when you're dealing with MySQL, pretty much the limitations of schema updates are whatever you can convince a DBA to run for you. But BigQuery has a lot stronger limitations. The one that we find the most that trips people up is that it's very easy to update a table in MySQL to add a new column that's non-nullable but has a default, and it will just backfill all that data for you. In the case of BigQuery, it has no concept of add a new column with the default. It's just if you add a new column, it has to be nullable. So when people update a source table, you add a new column with a default, when that tries to get into BigQuery, it will just fail, and we need to re-snapshot the whole table all over again. So optimistic writes, so this just means that as soon as a Kafka connector gets data, it will attempt to write them. It doesn't wait for basically the Kafka Connect framework to ask it to commit the data. It will just optimistically try to write everything. This results in quicker writes. It's particularly useful during snapshots when there's a whole bunch of data coming in. We're finding that in a lot of cases, without the optimistic writes, snapshots would end up, a job would basically take too long. We get that rebalancing I talked about before. It took a lot longer than it really should to get data into BigQuery. Excuse me. BigQuery has partition tables, which just allows for more efficient access, particularly if you're looking at particular days worth of data. And so we have the option to write to daily partitions. BigQuery doesn't have any other option other than day partitions, so that's the one we use. And then sort of a newer sort of beta feature we have for Kafka Connect BigQuery is instead of streaming, we have the option of going through Google Cloud Storage in a batch format. So we still get the information via streaming, but instead of directly writing it to BigQuery, we write as much as possible to GCS and then run a GCS load to BigQuery. So you may wonder, wait, I thought we were trying to get away from batch. So the issue that we found is for particularly large tables, there are limits on how fast BigQuery will allow us to stream data, or sorry, Google will allow us to stream data into BigQuery. GCS to BigQuery batch loads don't have any limitation like that. So you are limited by Google if you're doing these streaming issues, if you're just going through streaming, which I will emphasize is not, we have not found it to be an issue for any normal table. It's just an issue during snapshots. But we found that this is particularly useful for bootstrapping very large data sets, in which case you don't really care about the streaming aspect all that much. You're just trying to get the initial data in. And then when the bootstrap is completed, you can just switch off the GCS option and it will go seamlessly into streaming. Okay, so we talked about how we get all these, DML events into BigQuery, but we really haven't explained how we get those to look like exactly what's in MySQL. So for that, we use BigQuery views to sort of compress the data. So basically, we want to go from this to this. In the case of like something like this, where we have like a whole bunch of useful metadata, what we essentially do is we we deduplicate on ID. We just, we deduplicate on ID and just pick the most recent time. In our case, actually, well, so you can do most recent time. We also have additional information about when it got into Kafka. That's the Kafka offset. We actually deduplicate on that. That's a little bit of extra metadata that KCBQ can put into your events for you. Another nice thing about doing this with views is that you can easily remove sensitive information. So this contains sensitive information, and maybe that's available to some people, but perhaps you want other people to have access to this data, but not the sensitive data. You can just create a view that doesn't include the email. Voila, we have less sensitive data in here. All right, future work. So we are, one of the biggest things we're doing right now is that this traditional ETL system I talked about at the beginning is still basically the majority of what we do for our monolithic database. And we're in the process of migrating from that system to the streaming pipeline for Monolith. One of the big things we had to do here, I talked about that, that sort of online rebootstrapping of individual tables. That was really important for Monolith because rebootstrapping just one of the monolithic database tables took like on the order of a week. So that's not something we want to have to do regularly at all. We want to be able to add to connectors and only rebootstrap those tables as needed rather than constantly rebootstrapping everything. Another open issue is that is specific metrics for KCBQ. So you can get metrics like generally for a connector, but we cannot add at the moment specific metrics for KCBQ. So there's like general metrics about, how much data is flowing through the connector and stuff like that that's built into Kafka Connect, but there's at present no way for an individual connector to write metrics specific to its implementation. So I talked a little bit about potential compatibility problems. So if you are just in the Kafka environment, the schema registry can be configured to run compatibility checks and make sure basically no schema update happens that would result in problems. But when you sort of exit that and go into the MySQL layer, we're outside of that, and a DBA basically has the authority to just run anything. It's totally possible, and it's happened a number of times that a DBA has made a MySQL change that has resulted in the pipeline going down, which is a little bit frustrating. It'd be really nice if we could notice and prevent changes at the MySQL layer that would prevent this sort of thing. And there's a link to a open issue on Debezium for that. And let's see, okay, cluster scaling. So the image I gave before of our architecture is pretty close to literal. We have exactly 2 Debezium MySQL replicas and 1 cluster. But in the future, that may not be enough. We've actually already run into a couple of times where the replicas, we've just sort of been bumping up the memory and it's still fine. So we've stuck with the 2. And as far as a single cluster is concerned, in general, the single cluster works just fine. When we notice the most problems is when we end up in the situation where we're rebootstrapping, or sorry, not rebootstrapping, when excuse me, when Kafka Connect decides it needs to rebalance. One of the biggest issues for this is like if you add a new connector, the new connector will spend a lot of time at the beginning rebalancing. That kind of puts a ton of load on the cluster. And so adding new connectors and modifying connectors is still kind of a pain. So we may have to do something about that relatively soon. But the frustrating thing is normally it's totally fine. But anyway, that's a couple of issues that we've seen that we may have to look into. So we have a blog post on this if you want more details. It was written a while ago, but it's really super useful. It has a lot of the fine details that I didn't go into here. And if you'd like to look up KCBQ on GitHub, it is there. And that's it. Any questions? Yes? Just a second. Could you pass this back?
Could you go back to the Debezium architect, the MySQL Debezium Kafka architecture slide?
Sure. This one?
Yes.
Okay.
So when you have like the primary and the secondary replicas, does only the primary one feed into the proxy?
No. I mean, but what I'm sort of using this to illustrate is that the proxy is picking the primary Debezium replica to feed into the individual connectors. So only one of the replicas is actually used at a time. The other one's just there, in case there's a failure.
In case there's a failure. Okay. And then when you went to the open issues with the cluster scaling, if the proxy is still only pulling from 1, it's still kind of fuzzy where the tertiary or the extra replicas would benefit the proxy drawing. Is it because the primary and the secondary are still likely to fail, or?
I guess that's a good question. I feel like the major issue is actually, and I don't think I necessarily illustrated that well. So the problem actually is the fact that, so you notice that there's 2 replicas, but I have 3 microservices here. In practice, there's n microservices, and they're all replicating into these 2 replicas. The bigger issue there that I sort of see is that the log messages the bin log messages that these connectors are receiving are actually literally all the bin log messages, and they're filtering out 95% of what they see because they only care about certain microservices data. So it would be more like instead of like adding like a third, like more like add like, you know, another 1 and a 2 that are only for a smaller set of microservices.
Okay.
Yeah.
I think I see where you're getting. Thank
Okay. Anything else? All right then.